Hey everyone, Mrs. Basega here, and today we're looking at the different spectra of light. Previously in class, we've sorted these into two categories. That is either continuous spectra or bright line spectra. And we've gone around the room to see what types of light give off what types of spectrum. Now, with these, we had the chance to look at a lot of different lights, and a large number of them were continuous spectra. These would be things like the sun, heat lamps, the light above the fish tank, the flashlight from your phone. These are continuous spectra because these are lights that use heat to create light. Now, these might still run on electricity, but the heat of them is what creates the light. If you think of an incandescent light bulb, when it's talking about its heat, well, that's referring to the temperature spectrum that it's putting out. Continuous spectra always look white, but have you ever noticed that all white light is not the same? Sometimes it's a bluish white or a yellowish white. Well, that comes because that our brain sees the color white whenever we see a combination of red, green, and blue all put together. So when we see white light from the sun, it's centered at yellow and makes a continuous rainbow because of its temperature. A red giant would have a spectrum centered at the color red, so it would have some green and blue lights, mostly red and a lot of infrared. Notice that this star would have to be cooler because it's putting out red light, which has less energy. Hey, a blue dwarf would center along blue and require an even higher temperature and put out a lot more ultraviolet light. Now, we're not going to do lots of math about continuous spectra because for these, I'll save this for your astronomy classes. The connection between the or wavelength peak and the temperature that the star puts out is something you'll deal with later. On our end, you should know that hot objects emit light that's continuous. All the colors of the rainbow are present, and that the color of the light depends on the maximum wavelength that's peaked here. Now, all the other instances like the laser, the fluorescent light, the light that was like the hydrogen gas or the neon gas or the mercury gas in the tubes, well, those bright line spectra occur because electrons in very specific excited atomic states emit specific frequencies. For instance, neon has a bunch of little paired frequencies, and that has to do with its atomic energy levels. So in order to understand light, you have to first understand the electron. So let's check out a model of the atom that you should be pretty familiar with. This is called the planetary model. And in the planetary model, you have the nucleus in the middle, and the electrons are in these nice circular orbits on the outside. What quantum mechanics says is that there's only specific radii and energy levels that work, and nothing else does. Not only that, but the electrons don't exist between energy levels. And to put it this way, think about if I had an electron move from this excited state to the stable state. If this were a physical object, the electron would sometimes be here and would sometimes be here and would sometimes be here, but it's not. Because it's an electron, when it goes from one state to another, it simultaneously disappears from the outer shell and reappears at the inner shell with the new energy. Okay, so that looks like energy is destroyed because you've moved to a lower energy state. You've decreased your potential energy. So where does the rest come from? Well, that, my friend, is where we get into the light. As the electron transitions from a high energy state to a low energy state, it creates a light. And since there are only certain energies, that means my lights only have certain energies themselves. With only these specific energy levels of electrons, you get lights with predictable energies. We're going to redraw this, and notice the words on this side are the same as the last side. We're going to redraw this as, instead of a circle, like we had here, we're going to redraw these energy states with the innermost radii representing the ground stable state and all my excited states farther up. So first off, we have names for the different energy levels. The ground state is the n=1 state. It is the most stable of the states. So when I'm doing my labeling here, I would call this bottom state n=1. The next state is excited. This is n=2. So right now I have 2 electrons sitting here in the n=3 excited state. They each have an energy of -1 electron volt. And in case you haven't seen this before, 1 electron volt is a very, very small unit of energy. It's something like 10 to the -19th joules is 1 electron volt. So an electron volt is a very small unit of energy. Let's do this model of light emission. When we have this electron here, the electron goes from the n=3 excited state, and it's like, nope, we want to go to the ground. Disappears from this energy state and reappears at the ground, but now it has less energy. And as a result, it has to put off a beam of light that makes up for it. How much energy is there? Well, that's easy. The energy is equal to the absolute value of the difference between the energy states. So if the ground state was 5.5 and the excited state was -1, and we absolute value this, so it doesn't super matter the order, I see that the purple light must have had something like 4.5 electron volts of energy. So let's do this again, and we'll repeat this with our other electron. As our other electron tries to transition to the ground, it doesn't go the whole way the first time. This time, it transitions from the n=3 state to the n=2 state. How much energy do you think it puts off then? That's right, 2 electron volts. And because 2 electron volts would be less energy, I'm going to draw this wave with a longer wavelength. Red has a longer wavelength than violet, and this would have 3 minus 1, or 2 electron volts. So we only have one transition left. Let's say that let's say that an electron wants to go from here down to the ground state again. How much energy does this light put off now? That's right, 2.5, because it goes from 3 down to -5.5. The difference between those two, if I subtract and remember to take this absolute value, is going to be 2.5 electron volts. Since that's a little bit more energy than red, I chose green as my color, and I'm going to draw it with a slightly smaller wavelength. So this item, or this atom, would emit 3 colors in its bright line. It would have 1 bright line of purple, 1 bright line of red, and 1 bright line of green. What we should think of here is that energy is conserved when an electron moves to a ground state. So as the electron moves from an excited state to ground, it emits light with a certain energy, so that energy is conserved. We can calculate that energy by subtracting the final and initial energy levels in electron volts and then taking their absolute value. From here, we're going to work on homework 10.5, or something similar, in which we're going to look at the hydrogen atom. In the O physics simulation, I want you to calculate the energy from the different levels. So let's say we have an energy level that starts at energy level 6 and moves to energy level 2. This emits a violet wavelength of light with a 410 nanometer wavelength. We can measure its wavelength on the screen, and we can calculate its energy. In this case, to calculate the energy, this would be something like 3.4 electron volts minus 0.378 to get the total energy of this transition. Now, if you notice that you go to a transition and it doesn't give you a wavelength with a color, Notice in this case, the wavelength is black and it says the photon has a wavelength of like 397 nanometers. If it's showing up as black instead of a color, that means that this color, this wavelength, is not in this human visible spectrum. And so you have to determine, is that ultraviolet or infrared? All right, everyone. So it is about that time. Best of luck.